Hi everyone. So in this video, we're going to talk about confidence intervals for a population mean. And we're going to start by looking at the pattern that we learned about with sampling distributions. I am going to warn you though that unlike with proportions, there is a little bit of hiccup that happens with means that will mean that we need to have a different distribution than the normal model. So there's quite a bit of explanation here in the beginning before we actually do some problems. So first we have, this is the sampling distribution for X bar. Right? We know that the population mean is in the middle and that each standard deviation is the standard deviation of the population divided by the square root of n. And we know that 95% of the sample means are going to be within 2 standard deviations from the population mean. So we can use this same idea when we have just a single sample and we're trying to make an inference about the population mean. So if I take a single sample and I have one X bar and one standard deviation for that sample, where is that X bar that I just found? Right? I don't know if it's above or below the population mean. I don't know if it's close to it or far away. But just like we learned in the videos with proportions, that talking about a distance doesn't really matter who's at the center, right? So if I say that 95% of the X bars are within 2 standard deviations of the population mean, then I can also say that if I have X bar at the center, that there's a 95% chance that the population mean is within 2 standard deviations of X bar. The only problem is that when we calculate the standard deviation, we're using the population standard deviation. But if I'm taking a sample, I don't have the population mean or standard deviation. I only have the sample mean and the sample standard deviation. So just like we did with proportions, I'm going to use what I have, which is the sample standard deviation. And so instead of calling it a standard deviation, we call it a standard error. And we use the sample standard deviation divided by the square root of n. The difference is that we have kind of an extra variable. So if you recall back to proportions, we could use the population proportion to calculate the standard deviation. And therefore, when we had a sample proportion, we used that to calculate the standard error, but we only had that one variable, the proportion. Now when we take a sample, we have 2 variables. We have the mean and the standard deviation. And this extra piece has kind of caused a little bit of a hiccup. So up until about the early 20th century, people were using the sample standard deviation to calculate the standard error, and they were just using the normal model. But some people started to realize that it wasn't working for smaller sample sizes. So I'm trying to make this long story kind of short. This guy named William Gossett was actually a brewer for Guinness in Ireland, and he did a lot of experiments in making the beer consistent, right? So he wants to make sure that every Guinness beer tastes the same every time, but also making it taste really good, right? So he does a lot of experiments, but it takes a long time to grow hops or set up these experiments. So a lot of times his sample sizes were very, very small, like sample sizes of 3 and 4. And when he tried to apply the normal model, it wasn't working right. So this guy basically asked Guinness if he could take a leave of absence and go back to college and study statistics and figure out what's going on. And they said, sure. So he did, and figured out a new family of models that accounts for this smaller sample size. So then he figures all of this out, and he wants to publish and tell everybody else what he's learned, and Guinness says, no way, you're not allowed to publish. So he argues with them a whole bunch, and they finally give in and say, okay, you can do it, but you can't use your real name and you can't use our name. So his boss made him use the pseudonym, or the, what's it called? Pen? I don't know. I'm not an English person, but he uses the fake name Student. So his models are called Students T models. So it has nothing to do with students. It just has to do with what his boss made him sign his papers as. So what he did was he found that there were, when the sample size was small, that there was a higher likelihood that you could have a sample mean that was further from the population mean. So what you're seeing here is, like if I look at this middle one, the height of this unimodal distribution, the height of this model is not as high as the normal curve in the middle, but you can see that on the ends, there's more space between the model and the x-axis because there's a higher likelihood that the sample mean can be in these more extreme areas when you have a smaller sample size. But as the sample size gets larger and larger, these t distributions get closer and closer to normal. We use a term called degrees of freedom to describe which family of t distributions we're using. And degrees of freedom is pretty straightforward. It's just the sample size minus 1. So if you have a sample of 7, then the degrees of freedom is 6. And really this just allows people to describe which family they're using. We can still find the mean and the standard deviation in the same way, and there's a lot of things that are very similar between these distributions and the normal model. But what this does is it changes our critical value. So when we were working with proportions, we had a z star here. But now we're not using a normal model. We're using the students' t models. And so we use a t star here. It works basically the same way. It's like a t-score instead of a z-score. It talks about the number of standard errors that from the sample mean, and it depends on the confidence level. So it really works exactly the same, but we call it a T instead of a Z. I'm not going to do any of these by hand. If you really want to, you can look at that second vars, that distribution command, and you'll see that there's a T CDF and an inverse T that allow you to do similar problems as we do with normal CDF and inverse norm. But that's not the point here. The point is to be able to create a confidence interval and to interpret it. So these confidence intervals will have the same assumptions and conditions as the sampling distribution for means. But the last one, we give it a name and we call it the nearly normal condition. But again, it's that idea that if the sample size is fairly large, greater than 30, then we are safe to assume that we can apply these T models. But if the sample size is pretty small, then we want to make sure that we don't have any major outliers or a really strong skew. So it's really good to look at a box plot and make sure that it's quote-unquote reasonably unimodal and symmetric, and there's a lot of leeway there. You basically want to make sure no outliers or major skew. Okay, so we're not going to do anything by hand. We're going to use our calculator for these, And the interesting thing about the command for these types of intervals is that we can either use statistics that are given to us or data. So we're going to do both of those examples. So here we have a random sample of 55 community college students were asked how many hours a week they work at a job. The sample mean was 13.62 hours with a standard deviation of 5.37. Construct a 95% confidence interval for the mean number of hours community college students work in a week. So we're going to look at the assumptions and conditions first. We're told that this is a random sample. 55 is definitely less than 10% of all community college students, which means that it's safe to assume that the individuals within this sample are independent. And then 55 is greater than 30, so we don't have to check anything. We can say, yep, this is large enough, it meets that nearly normal condition. We can use the T models. So this means that it's safe to use those T models, and we can look for a one sample T interval, which is the formal name of this, but in our calculator it's just called a T interval. And I'll show it to you here in a second. So we're going to go to the same place. We're going to go to stat and then tests. So go to stat, tests, and the T interval is number 8 there. I just want to pause this really quickly. See that Z interval command? We will never, ever, 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 ever use that. But I constantly see mistakes where people are using that command. We'll never use Z interval. So once you get there, we have the option of data, or underneath this black square it says stats. In this case, we're given the mean and the standard deviation, so we know the statistics of the sample. So we're going to choose stats. And then to write out your work, you're just going to tell me what you entered for each thing. And notice that if you keep track of the symbols and know that we are talking about a sample mean of 13.62, a sample standard deviation of 5.37, a sample size of 55, and then a C level of 0.95. And then we can calculate. And so we'll get an interval of 12.168 to 15.072. So we are 95% confident that the true mean hours worked by community college students is somewhere in this interval. So let's look more at that interpretation on the next page. I don't know why this doesn't, there we go. Okay, so I've got the same problem up above, and the answer that we just found, the confidence interval, is here. So that interpretation, again, is that we are 95% confident that the population mean hours that community college students work per week is between 12.2 and 15.1. A couple things you want to make sure that you are saying here. You're talking about the average number of hours worked by community college students, not the likelihood of individual community college students working this many hours, right? So this is the population average that we're looking at here. It says community college officials in California are warning students that working more than 15 hours a week can hurt grades and delay graduation. Does your sample contradict the claim that students are working more than 15 hours a week? No, it doesn't, because that 15 and slightly more than that is within the interval. So be careful here. I know that most of the interval is below 15, but that does not matter. 15 or 15.1 could be the population mean, and therefore our interval does not contradict the claim that students are working 15 or more hours in a week. If we increase the confidence level to 98%, does the interval get wider or narrower? So remember that if you want to be more confident, you need a larger target, which means that your interval will be wider. So the other thing that we can do with this command is that we can run a confidence interval when we just have the data. So in this case, it says the following are weights in pounds of 12 randomly sampled 2-month-old girls. Construct a 90% confidence interval for the mean weight of 2-month-old girls and interpret the results. So the first thing we want to do is make sure that these assumptions and conditions are met. We have a random sample. Oops, don't start yet. Not ready for you yet. All right, we have a random sample. 12 is definitely less than 10% of all, not community college students, of all 2-month-olds. And therefore, it's safe to assume that the individuals in the sample are independent. But we have a sample size of 12, which is pretty small. So before we go and find the confidence interval, we want to make sure that there aren't any extreme outliers and there's not any kind of extreme skew. So I entered the data in L1. Let me rewind this again. So remember that you go to Stat and Edit, and then enter the data in L1. Now the first thing I'm going to do is look at a box plot. So I'm going to use this stat plot to turn on the box plot, and then stat zoom or zoom 9 to look at the graph. So we did this in some previous chapters. So we're going to go to stat plot. I'm going to make sure that plot 1 is turned on. And you want the box plot that gives, you want the box plot that gives outliers. What is going on? There we go. So you want that middle one. And once you have that highlighted, we can go to zoom 9. So we go down to the zoom stat to look at the box plot. There's not any outliers. I know it's not, hold on. I'm sorry, you guys. Trying to get back, come on. It's so sensitive, there we go. There's not any outliers. I know there's some skew there, but it's not any kind of major skew. This is pretty close to symmetric for being as small as it is. So we would say that this meets the nearly normal condition. So from here, we want to use the t-interval command, but this time we're going to use data. So you're going to go to stat and tests and go down to that t-interval command. And again, you're going to enter data and then L1, leave the frequency as 1, and we have a C level of 9.9. So we had our list at L1. The frequency, you will always want to leave this as 1, and then our C level was 0.9. And we got an interval of 10.464 to 12.329. Remember that you're finding averages here, so don't write any kind of percent symbol or anything like that. All right, so let's go to the next page so we can interpret this. Actually, I don't know if I have any room. No, I don't. Let's interpret it here. So we'd say we are 90% confident that the population mean weight of 2-month-old girls is between 10.5 and 12.3 pounds. So I just wanted to review the margin of error when we're doing these problems. So if I have the confidence interval here. Remember that when you're finding the margin of error, that it's the distance between either edge of your confidence interval and the sample mean that is directly in the center. But we usually do this by subtracting the upper bound and lower bound of the interval and dividing by 2. So in this case, we have a margin of error of 0.9325. It's pretty big. How can we keep the confidence level the same but reduce the margin of error? So if I want to keep it at 90%, but I'm saying this is a really big margin of error, how can I fix that? Remember that the biggest thing you can do is make the sample size bigger. According to the National Health Statistics Report, the mean weight of 2-month-old boys is 11.5 pounds. Based on your confidence interval, is it reasonable to believe that the mean weight of 2-month-old girls may be the same as that of 2-month-old boys? Explain. We would say yes, 11.5 is within the confidence interval for the mean weight of 2-month-old girls, so it's reasonable to believe that the mean weight of boys and girls at this age are the same. All right, so looking at just one more example here, and this is just more of a conceptual example. There's no real math to do here. It says 2 people are going to construct confidence intervals from different simple random samples. Both confidence intervals will have a level of 99%, but one will use a sample of size 40 and the other will use a sample of size 120. If the samples are drawn from the same population, which confidence interval will have a larger margin of error, or will they both be the same? Well, a larger sample size will have a smaller error. Remember that the larger the sample size, the less deviation there is, the less variation there is between the sample means. So the sample with a smaller size will have the larger margin of error. Which confidence interval is more likely to contain the population mean? Or are they both equally likely to do so? So regardless of the sample size, you'll still be 99% confident that the population mean is within the interval that you found. You'll just have a smaller interval with a size of 120 than if you have a sample size of 40. So they're both equally likely to contain the population mean. All right, I'm sorry about all the mix-ups with how I'm explaining stuff in this video.